the grasp of gravity that Newton had was sufficient to enable us to travel from the Earth to the Moon. Ever find yourself disoriented in time's constant march, questioning if our comprehension of it is merely the surface of a deeper mystery? His discovery is more than just a hypothesis, it's a key that could unlock the revelation of a universe's secrets, more intricate and awe-inspiring than we ever imagined. How does Brian Cox's novel theory challenge our traditional conceptions of time, and what might it imply for our perception? Join us on a fascinating journey through the complexities of time as we investigate Brian Cox's recently revealed revolutionary theory about the nature of time in the vast cosmos surrounding us. Riddles are waiting to be solved, many of which focus on strange aspects of time and gravity, both integral facets of our existence. They depict a world where time behaves oddly, it can either slow down or speed up. In addition, it's possible that the force that keeps us grounded is not what we think. This is the realm of Albert Einstein's theories of relativity, where our perception of time and gravity unexpectedly changes. Albert Einstein, a name familiar to all, presented us with a fresh perspective on the universe through his relativity theories. His work laid the groundwork for comprehending the behavior of time under various circumstances, especially when moving at breakneck speed. It all began in the early 20th century when two revolutionary ideas were introduced by Einstein, concepts outlined in the special theory of relativity and the general theory of relativity. The special theory of relativity, published in 1905, changed our perception of the universe. To put it another way, it asserts that the physical laws remain consistent for all non-scientific observers, regardless of their motion. This theory introduces the concept of relativistic outcomes, like the well-known idea that time can stretch or slow down in certain situations. One captivating thought experiment often used to explain time dilation is this. Imagine being inside a light clock on a spacecraft moving at an extremely fast speed near the speed of light. Inside the spacecraft, a light beam is bouncing between two mirrors that are parallel to the direction of travel. As determined by the speed of light and the laws of physics, the speed of light remains constant for all observers. So, the light beam has to appear as if it is following a longer diagonal path, which leads to the outside. Keep an eye on how long it takes for the light to traverse the path. It should be identical for both the observer inside the spacecraft and the one outside. However, because the route is longer for the outside observer, it appears to require more time for the light to complete its journey. This apparent time difference between the two observers is what Einstein referred to as time dilation. The observer inside the spacecraft experiences slower time relative to the stationary observer. In this case, time behaves differently depending on your velocity. Understanding how objects change when they move quickly, also known as relativistic effects, is not just a theoretical concept. Scientists use large machines, like particle accelerators such as the Large Hadron Collider, to propel particles to near-light speeds. When objects move at such high speeds, we must take into account time in a special way to make precise predictions. Albert Einstein's measurements introduced a unique theory of relativity in 1905, and it revolutionized our understanding of the universe, particularly with regard to time and movement. This theory challenges what we might intuitively believe. It states that the principles of physics are the same for everyone, even if they are not at rest. This differs from our everyday experience, from which we might infer that if something is already in motion and we add more speed, it simply gets faster. However, according to Einstein's theory, there is a maximum velocity that nothing can exceed, the speed of light. In this context, things that we see happening simultaneously may not appear identical to everyone moving close to the speed of light. A different idea that comes from this special way of thinking is length contraction. This means that an object appears to be shorter in the direction it is traveling when viewed from a stationary position. Additionally, there's the famous equation, which demonstrates that mass and energy are compatible. This is essential for comprehending the behavior of minute particles when moving at high speeds and also for explicating nuclear processes. In the real world, special relativity isn't just an abstract idea. It's something we rely on in everyday technologies such as GPS. When GPS satellites send signals to your device, they are in motion, and due to this, the passage of time changes slightly for them. If we didn't account for time dilation in our GPS calculations, your location data would be significantly inaccurate. Thus, special relativity teaches us that time is not uniform throughout all locations and circumstances. It depends on how things are moving. This notion challenges our usual conception of time and space. It appears as though our conventional view of the universe is a bit flawed. According to the special theory of relativity, time isn't constant. It is influenced by some fundamental movement ideas, such as the constancy of the speed of light and the relationship between mass and energy, which have been established by numerous experiments. However, there's more. Enter Albert Einstein's general theory of relativity from 1915. This theory delves deeper into the connection between gravity and the structure of the universe. It reshapes the traditional idea that gravity is just a force that attracts things. Instead, it proposes that gravity arises because space and time are twisted or curved. It's like saying gravity isn't an invisible force, it's just how things naturally move in the universe, as seen through Brian's interpretation. General relativity requires an understanding of the universe as a four-dimensional entity, combining 3 dimensions of space and 1 temporal dimension. Within this model, big things like stars, planets, and even the United States have an impact on space curvature and all the time in their vicinity. This curve is what we perceive as gravity. Imagine space-time is like a huge, flexible sheet. When Earth-sized objects are placed on it, they cause a depression in the sheet. If you place something smaller, like a ball, near the depression, it will roll toward it. This is similar to how objects behave due to gravity, not because of some invisible force, but because of the bending of spacetime. General relativity offers a robust explanation for the movement of objects in our solar system, such as the orbits of the planets around the Sun. It can precisely predict the paths these planets follow. For example, Earth orbits the Sun in an elliptical pattern. Brian says that this contrasts with the old idea of gravity simply bringing things together, which struggle to explain how planets behave. According to the new theory, space and time are curved in the same way that a flexible fabric behaves. The detection of gravitational waves marked a major breakthrough in physics, confirming that Einstein's predictions were not only theoretical but also observable. These waves are disturbances in spacetime caused by some of the most violent and energetic processes in the universe, like the collision of black holes or neutron stars. Their discovery opened a new window into the cosmos, allowing scientists to study astronomical phenomena in ways that were previously unimaginable. Einstein's work on general relativity has also influenced our understanding of the universe's large-scale structure. For instance, his theory helps explain the expansion of the universe. Observations of distant galaxies show that they are moving away from us, suggesting that the universe itself is stretching. This discovery, made in the 1920s by astronomer Edwin Hubble, was one of the key pieces of evidence that led to the development of the Big Bang theory. The idea that the universe is expanding was a revolutionary thought, but it fits perfectly with Einstein's equations of general relativity. In the decades that followed, scientists continued to build upon Einstein's ideas. They have developed models of the universe that incorporate dark energy, the mysterious force responsible for the accelerated expansion of the universe. These models suggest that the fabric of spacetime is not only curved by massive objects but that the rate at which the universe expands is also influenced by an unknown form of energy that pervades all of space. In addition to the cosmic scale, Einstein's theories also have practical applications. Technologies such as GPS, which are crucial to modern life, rely on the principles of relativity. GPS satellites orbit the Earth at high speeds and experience weaker gravity than objects on the Earth's surface. To ensure that GPS systems provide accurate location data, engineers must account for both the time dilation effects due to their velocity and the difference in gravitational time dilation between the satellites and the Earth. Without taking these effects into account, GPS systems would be off by several kilometers. As we continue to explore the universe, the implications of Einstein's theories extend beyond practical applications. His work challenges our perception of reality itself, forcing us to reconsider the nature of space, time, and gravity. His theories continue to inspire new questions, and with each discovery, we move closer to understanding the true nature of the universe. Whether it's through studying the behavior of black holes, the bending of light around massive objects, or the expansion of the universe, the mysteries of spacetime are far from being fully unraveled. The journey of scientific discovery is ongoing, and each new step brings us closer to a deeper understanding of the cosmos. Through these revolutionary ideas, Einstein has left a legacy that continues to shape modern physics and our understanding of the universe. His theories are not just academic exercises, they are the foundation upon which much of our current understanding of the universe is built. As we venture into the unknown, we can only wonder what future discoveries will bring and how they will expand upon the groundbreaking work of one of the greatest minds in history. A lot of tests demonstrate that general relativity is accurate, whether through planetary observation, the bending of light, or the detection of gravitational waves. Relativity continues to be a solid and trustworthy framework, while claiming that gravity is a myth may seem shocking, in particular, since we experience it every day. In the field of physics, it is common to contest and re-evaluate established theories. Scientists like Brian regularly challenge established wisdom, and in the domain of gravity, according to some, alternative perspectives and a theory that questions traditional gravity is modified Newtonian dynamics indicates that gravity acts differently at low speeds, especially in galaxies, without the need to invoke dark matter. Instead of positing invisible matter, it suggests that gravity strengthens at slow speeds. The enigmatic concepts of dark matter and dark energy, which were introduced to elucidate certain cosmic phenomena, are also involved in the discussion of gravity. Critics argue that these ideas may be ineffective and that alternative explanations for our observations exist. Some scientists oppose the new directions that Einstein's theory of gravity might take, proposing theories involving unknown forces or particles that could alter or enhance our understanding of gravity. It is essential to acknowledge that, in science, novel concepts are not discounted out of hand. Rather, they undergo rigorous testing to see if they are valid. For instance, Einstein's concept of time is part of a four-dimensional continuum, where time travel may be limited by the speed of light. This has been creatively explored alongside shortcuts and wormholes. For example, Stephen Hawking's chronology protection theories suggest that time travel into the past is unlikely from a physics standpoint. Ongoing experiments and observations aim to determine whether these new theories can explain phenomena, like gravity, in a manner consistent with our current understanding. While many thoughts have been given to these ideas, none have convincingly replaced the well-established principles of gravity. Questioning and rethinking established theories is an essential part of advancing scientific knowledge, fostering research, and developing a deeper understanding of the universe. Within the gravity field, the theories of general relativity remain the most important and successful. Despite challenges and competing ideas, it consistently performs well in tests and explains a variety of phenomena, such as planetary motion and the bending of light around massive objects. General relativity endures because it is simple and accommodates a wide range of phenomena. As discussed, according to Einstein's special theory of relativity, time can behave differently depending on speed. Now, let's explore how this idea affects actual situations, particularly in the field of space exploration. It is thrilling but difficult because space is vast, and according to Einstein's theory, the speed of light is the fastest potential speed. This makes traveling between stars a major challenge, even with cutting-edge technology, because of the long travel time necessary to even reach the closest stars. To comprehend what occurs to time when traveling through space, think about the well-known image of the twin paradox. One twin remains on Earth, while the other twin embarks on a fast journey to a distant star. When the traveler returns, they discover that less time has passed for them than for the twin on Earth. They have essentially entered the future. Time is critical for space travelers because, the longer the trip, the more time slows down. If astronauts were to visit nearby stars where time slowed significantly, they would age more slowly than people on Earth. While this may seem like science fiction, it's a real effect that relativity predicted. Imagine humans sending a crew to a star system far away. Due to the vast distance, the journey could span many years. Even if they travel quickly, the astronauts aboard the spacecraft would experience time more slowly because of the time dilation effect. However, from Earth's perspective, much more time would pass. Time dilation also affects not just living beings, but technology. Devices for communication and computers on spacecraft must account for time dilation for accurate operation. High-speed space travel results in physical challenges such as isolation, exposure to radiation from the cosmos, and the mental health toll of being far from Earth for an extended period. In our everyday lives, we can observe the effects of time dilation in the Global Positioning System, GPS. GPS depends on the precise timing of signals from moving satellites. Since these satellites experience time dilation, it's vital to factor in these effects for accurate GPS readings. Neglecting this would lead to substantial errors in navigation. Now, let's examine why time follows only one direction. Our lives move from the past to the present and into the future. This one-way passage of time is fundamental to our understanding of truth. But why does time possess this one-way nature? To comprehend this, we turn to the concept of entropy, a measure of disorder or randomness in a system. Entropy, which is associated with the arrow of time, tends to increase as time passes, driving time to move in one direction. The second law of thermodynamics expresses this relationship, stating that in any closed system, total entropy will either increase or remain constant. In simple terms, entropy naturally tends to rise and never decreases on its own. Observing how things advance toward chaos around us helps us see the one-way flow of time. Picture a deck of cards arranged neatly. If we shuffle them, this change causes them to become disorderly. This transition from order to chaos illustrates the unidirectional nature of time, as seen in everyday occurrences like melting ice or stirring a cup of coffee. Time, as we experience it, is intertwined with the concept of entropy, which also plays a critical role in how we understand irreversible processes in nature. For example, the melting of ice or the cooling of a hot cup of coffee are classic examples of entropy in action. These processes move in one direction, toward greater disorder, demonstrating the arrow of time. We cannot, in normal circumstances, reverse these processes. The ice cannot spontaneously freeze back into a solid form once it has melted, and a cooled cup of coffee won't heat itself back up. This irreversible flow of time is more than just a philosophical or abstract concept. It has practical consequences in various domains of science and technology. For instance, the second law of thermodynamics underpins the operation of engines, refrigerators, and many other systems. In these systems, energy disperses in a way that increases entropy, and this provides a framework for understanding how we can convert energy from one form to another, but never with 100% efficiency. There will always be some loss, often as heat. In cosmology, the concept of entropy in time is crucial in understanding the fate of the universe. The idea of a heat death of the universe stems from the second law of thermodynamics, which suggests that, over an incredibly long period, all matter and energy will eventually reach a state of maximum entropy, where no useful energy remains to do work. This would signify the end of time, or at least the end of any kind of organized or structured events within the universe. However, the relationship between entropy and time also raises questions about the beginning of the universe. The Big Bang theory proposes that the universe began in an incredibly hot, dense state, with very low entropy. As the universe expanded, it cooled, and entropy began to increase. This trajectory from low entropy to higher entropy over time helps explain why we observe a universe that is increasingly disorderly and why time flows in one direction, from the past toward the future. Despite this, the nature of time remains one of the greatest mysteries in physics. While general relativity and thermodynamics give us a solid framework for understanding how time behaves on a macroscopic scale, there are still deep unresolved questions. For example, at the quantum level, time behaves in ways that challenge our conventional understanding. Quantum mechanics introduces phenomena that appear to defy the classical arrow of time, such as quantum entanglement, where particles separated by vast distances can instantaneously affect one another. Some theories even propose that time itself could emerge from more fundamental processes, rather than being a fundamental concept in itself. In these theories, time could be seen as a byproduct of the interactions between quantum particles or the flow of information across the universe, suggesting that time, as we experience it, is an emergent property rather than a fundamental aspect of reality. Thus, the study of time, whether in the context of general relativity, quantum mechanics, or cosmology, remains one of the most fascinating and profound pursuits in modern science. As our understanding of time deepens, it will undoubtedly continue to challenge our most basic assumptions about the nature of reality, the structure of the universe, and even the very fabric of existence itself. Time is not merely a measure of change but a concept that underpins the way we understand everything from the smallest quantum interactions to the largest cosmic events. In conclusion, while much has been learned about time, space, and gravity, the mysteries of time remain vast and open to exploration. As scientists push the boundaries of knowledge, they will continue to confront the question of time's true nature, with each discovery paving the way for a deeper understanding of the universe and our place within it.